So now let's look at the parabola. Quantity y minus k squared is equal to 4 times a times the quantity x minus h. The parameterization for this parabola is given by x of t is h plus at squared, and y of t is k plus 2at. And so x prime of t is 2 times a times t, and y prime of t is 2 times a. And so the slope of the tangent line is given by y prime over x prime, which is 2a over 2at, which is 1 over t. So now the equation for the tangent line is y minus the quantity k plus 2at is equal to 1 over t times the quantity x minus the quantity h plus at squared. So we'll multiply both sides of the equation by t. So we have y times t minus k times t minus 2 times at squared is equal to x minus h minus at squared. So on the left-hand side, we have t times the quantity y minus k, and we'll move this at squared term to the right. And so we have x minus h plus at squared. Now, on the left-hand side, we want to have 2at, so we need to multiply both sides of the equation by 2 times a. And so we have 2at times y minus k is equal to 2 times a times x minus h. And for at squared, this is a specific value for x minus h, and so that's plus x sub naught minus h. Now 2at is a specific y value minus k, and so we have y sub naught minus k times y minus k is equal to 2 times a times the quantity x minus 2h plus x sub naught. Okay, so next we're going to look at the physical law, the law of reflection. The law of reflection states that the angle of the reflected ray equals the angle of the incident ray with respect to the normal to a surface. The incident ray, reflected ray, and the normal all lie in the same plane, and the incident ray and the reflected ray are on opposite sides of the normal. Now, the law of reflection holds regardless of whether the surface is curved. So the angle that an incident ray makes is the same as the angle that the reflected ray makes with respect to the normal. Now, because these two angles are equal, necessarily the angle that the rays make with respect to the tangent line to the surface are the same. And if the incident ray is not exactly along the normal, then these angles are necessarily acute angles. So let's use the law of reflection to analyze the reflective properties of the conics, and we'll start with the reflective properties of an ellipse. The reflective property of an ellipse is that a ray from one focus of an ellipse is reflected by the ellipse to pass through the second focus. So again, a ray from one of the foci of the ellipse is reflected by the ellipse to pass through the second focus. Now we can prove the reflective properties of an ellipse by showing that the angle that the ray from the first focus to the point of intersection makes with respect to the tangent at that point of intersection is the same as the angle made by the ray from the point of reflection to the second focus. Also notice that the tangent line intersects the horizontal line which contains the major axis of the ellipse. So let's sketch an ellipse beginning with some coordinate axes. And we'll choose to place this ellipse in standard position with center at the origin. And so a ray from the first focus is reflected at a point P with coordinates A times cosine of t, B sine of t, and it's reflected at that point to pass through the second focus. And the tangent to the ellipse at the point P intersects the x-axis at the point T. So we need to determine the coordinates for that point. So recall that the tangent line is given for an ellipse is given by the equation cosine t divided by a times x plus sine t divided by b times y is equal to 1. And the tangent line intersects the x-axis when y is 0. And so we have cosine of t divided by a times x is equal to 1, or x is equal to a divided by cosine t. And so the coordinates for the point T is a divided by cosine T, 0. Now the angle that the ray from the first focus to the point T makes with respect to the tangent, we'll call that angle alpha. And the angle that the ray from P to the second focus makes with respect to the tangent, we'll call that angle beta. We need to show that alpha and beta are the same. So ultimately, we're going to prove these angles are equal using the law of sines. And so we need to look at some side lengths of the corresponding triangle. So first, let's look at the distance from the point P to each of the foci. So the distance from the point P to the first focus is E times the distance from the point P to the directrix that corresponds to the first focus, and that is the directrix with the equation x equals a divided by e. And so this is e times a divided by e minus a cosine t, or a times or a minus a times e cosine t, which is a times the quantity 1 minus e cosine t. Now the distance from P to the second focus is e times the distance from the point P to the second directrix, which occurs at the line x equals negative a divided by e. And so this is e times a cosine t minus a negative a over e, or plus a over e. And so this is a times e times the cosine of t plus a, or a times the quantity 1 plus e cosine t. And so the ratio pf1 to pf2 is 1 minus e cosine t over 1 plus e cosine t. So let's recreate the triangle. This is the angle alpha, and this is the angle beta. So now we're going to look at the distance from the point T to each of the foci. Oops, I labeled the foci incorrectly. We're going to look at the distance from the point T to each of the foci. So first, the distance from T to the first focus is the x-coordinate of the point T, which is a divided by cosine t, minus the x-coordinate of the first focus, which is a times e. So this gives us a minus a times e times cosine t, all divided by cosine t, which is a times the quantity 1 minus e cosine t, all divided by cosine t. So now the distance from the point T to the second focus is a divided by cosine t minus the x-coordinate of the second focus, which is negative a times e, and so we have plus a times e. And so we have a plus a times e cosine t, all divided by cosine t, which is a times the quantity 1 plus e cosine t divided by cosine t. And so the ratio tf1 to tf2 is 1 minus e cosine t divided by 1 plus e cosine t. And recall that that is the same as the ratio pf1 to tf1, correction, to pf2. And so we can rearrange these ratios so that we have the ratio pf1 to tf1 is the same as the ratio pf2 to tf2. And so now we can apply the law of sines. So we look at the angle opposite the side pf1. So from P to F1, the angle opposite that side is PTF1. So we have sine of angle PTF1 over the side PF1 is equal to the angle alpha, sine of the angle alpha over the side TF1. And so the ratio PF1 to TF1 is sine of the angle PTF1 over sine of alpha. Now we look at the angle opposite the side PF2. Notice that is the same angle PTF1. So we have sine of angle PTF1 over PF2 is the same as sine of the angle TPF2 over the side TF2. And so the ratio PF2 to TF2 is the ratio sine of the angle PTF1 to sine of the angle TPF2. Now, since these ratios are equal, their ratios of their signs are equal. And since the numerator is the same in both ratios, we have the sine of A is equal to the sine of angle TPF2, sine of alpha rather, is equal to the sine of angle TPF2. Now notice that the angle TPF2 includes the angle alpha, and so those two angles are not equal. Alpha is not equal to angle TPF2, but since their sines are equal, that means that that angle TPF2 must be pi minus alpha, since sine of pi minus alpha is equal to sine of alpha. So now notice that the angle beta and the angle TPF2 are supplementary, since their vertex is on the same line, being the tangent line through P. And so we have that beta plus the angle TPF2 is equal to pi. And so beta is equal to pi minus the angle TPF2, which is pi minus the quantity, pi minus alpha. And so beta is equal to alpha as required.